Okay. Um, Welcome back. There are even some notes for this lecture. Oh, hang on. That's the homework, which is kind of fun. It starts from stuff we did last time, determinizing. We had this non-deterministic finite automaton, and from it we constructed this deterministic finite automaton, which looks a bit of a mess. And there's one thing I wanted to say about it before getting stuck in, which is that here we consider all possible sets of states of the non-deterministic machine. So the idea is that one state of the DFA represents a bunch of possibilities for the NFA. And we're asking, how does the next symbol affect the possibilities? And there's one thing that's important to consider that we didn't mention, but I did put it in the lecture notes, is that we don't need to consider all the possible subsets of the states, only those subsets which are epsilon closed. So that's to say, if you can, the epsilon closed sets are the ones you can't escape from by doing epsilons, right? By accepting no input, right? So clearly, if you're considering a subset that you can escape from with an epsilon, then there's somewhere else you could be. So that means we can rule out in this picture any subset which contains one but not two. So in particular, this one here, if you could see my mouse pointer, which you probably can't, the set which contains only one is not epsilon closed. If you could get to one, you could definitely get to two. Likewise, this 0 or 1 shouldn't be there because if you can get to 0 or 1, you could definitely also get to 2. And that's and where do you start from? You take the start state and then you grow it by everywhere you can get to by epsilons from the start state. That's the starting set of places you could be. See what I mean? So that's a crucial simplification. And actually, let's just talk about the homework. Well, actually, this lecture is going to be a big preparation for it, but you get a bunch of stuff, and we're going to talk about the thing we didn't talk about last week. So last week we talked about what even are deterministic and non-deterministic finite automata, and we talked about how to turn a regular expression into a non-deterministic finite automaton, and how to turn a non-deterministic finite automaton into a deterministic finite automaton by replacing it can choose this or that with consider all possible choices. But we didn't close the loop. So at the start of this lecture, we're going to close the loop. We're going to show you how to get a regular expression out of a deterministic finite automaton, to show that these are all three ways of talking about the same stuff. And then we're going to pay some attention to things that fall outside the power of regular expressions and these finite automata. So one of the things we're going to ask you to do, we're going to build some technology which computes a bunch of regular expressions, and we're also going to ask you to figure out how to simplify it. So in particular, you can see here, I've defined three functions, triple bar or triple and lowercase s star. And all they do at the moment is exactly the same. They do exactly the same thing as the constructors of the regular expression data type. In particular, they do no simplification whatsoever. But you know a bunch of laws that could make things less complicated if you thought about it. So you know, for example, that fail or P is the same thing as P, right? Adding an extra option that you can't actually win at is no help. Likewise, you know that null then P is just P. And you know things like star of fail is the same as null, right? You can if you can have any number of failures you like, the best number to choose is 0, right? So there's a bunch of ways, things you can do to make regular expressions simpler. And as you're going to build an algorithm that constructs a regular expression. If you run it with no simplification, it'll produce something big and awful. So if in the hope of getting readable output, you can work your way to cut it down. So your basic deliverable is to get as far as something which is big and awful but correct. And then the advanced deliverable is to cut it down. Okay, so what happens next? I've got notes for this lecture, which are flying off the screen, but it might at least remind us what we're up to. Okay. So the plan is yes. On one screen, you have a photograph of this piece of paper. And on the other screen, you have the same thing, only actually live. What we're going to do is teach you an algorithm for turning deterministic finite automata into regular expressions. And I don't know, have we had the word algorithm yet? I mean, okay, the word algorithm is really popular at the moment. It is misused by people who tell lies in a particularly malicious way. The word algorithm means a program which follows a strategy designed to get the correct answer. The thing that makes an algorithm is that it is provably correct. So when social media people talk about having an algorithm to show you the content you most want, they are lying. What they have is a heuristic, something that makes reasonable guesses, we hope. Something that's paid to shove propaganda in your face. Whereas, like me, I'm paid to shove propaganda in your face. Yeah, so the old version, so do you know algorithm is actually somebody's name? His name was, he was Al-Khwarizmi was his name. He was a mathematician in the Middle East, back when the entirety of civilization rested on the Islamic world remembering stuff everyone else had forgotten. And he invented a method for solving quadratic equations. You might even have been taught it at school, but you probably weren't. You were probably taught the quadratic formula at school. Were any of you taught a method of solving quadratic equations called completing the square? That was invented by Al-Khwarizmi. And it's it's a thing that you do. There's a set of steps that you take that are guaranteed to get the right answer. And that's why algorithms are called algorithms. Al-Khwarizmi also invented the idea that when you have an equation and if you know an equation is true and you do the same operation to both sides of the equation, it stays true. This is called the method of balancing, or algebra, as it's known. Al-Khwarizmi's contribution to our lives is enormous, but people are terribly prejudiced. So yes, algorithms are about methods that are precisely specified that deliver, that you can prove deliver. There are sometimes algorithms which say, we will get the right answer with probability 99% or something like that, and that's fine as well, right? As long as it's specified, and there's some explanation of why the thing does what's specified, rather than it just being kind of voodoo or cauldron of bubbling magic, which is what people. Right? Why do they call it an algorithm? They call this stuff an algorithm because they know that algorithm is an old word that conveys dignity on a computer program. And they want to steal that dignity even though they're not entitled to it. Rant over. Okay. So let's do something that's going to work, shall we? So before I drew this picture, I labeled these things 0 and 1. And then I realized, I was planning to do this on paper. And then I realized, well, 0 and 1 looks a lot like bits. So let's do it in ASCII instead with bits. Okay. So actually, of course, I will just copy this stuff down into an editor window. And I will make the font rather larger. And then also in the editor window goes this stuff. And now I hit right. So you can see I've got a test which actually works, even though we haven't done the definition yet. I recommend that while we work, we comment this out. But it's quite fun to run it from time to time and see how much computation you can get out of it, because that's a secret trick, right? When programs are not quite fully defined yet, Ask doesn't care. Ask will run as much as you've written and get as far as possible. Right. Okay, so what have we got? We've got our bits, which are playing the role of the states. We've got lists, because we need lists to control the algorithm. We've got our regular expressions, and here I have added infix declaration. So these two lines mean that or and then group to the right. And the fact that 4 is bigger than 3 means that then it is tighter than or, much the way you'd expect multiplication to be tighter than addition. So this is you learned stuff called like BODMAS at school. This is how you specify the same sort of rules in ASC. And the same is true of Haskell. Right. Okay. So our plan is to write. We're interested, if you look at the picture, we're interested in how to start at 0 and end at 0 after some input. Well, okay, clearly 0 or more inputs. But to figure out how to do this, we actually have to solve a slightly more general problem. We have to consider how to get from anywhere to anywhere else. And the trick to getting a grip on the problem is to control which routes we're interested in terms of which states we're allowed to pass through in between the start and finish. So what we're going to do is build up the picture a little at a time, right? How do we get from I to K? So these two inputs, the two bits, are where we're trying to start and where we're trying to finish. And we're hoping this regular expression will tell us all the strings that let us get from the start to the finish. And then the first input, which controls everything, is the list of states we're allowed to be in between I and K. So I is allowed to, I and K can be anything, but anything in the path between I and K, strictly between, has to be in the list. Okay, so you can see my test says, how do we get from 0 to 0, and the permitted states are all of them. So that if we get this right, we'll answer the question.
So let me point out something that's maybe obvious to many of you, but just in case it isn't. So Connor was using language talking about getting from one state to another state and passing through and so on. But what we are doing here, right, is we are trying to compute a regular expression that matches the strings that do what Connor said. Right?
Yeah.
So we have a finite automaton. We want a regular expression that describes the same strings as the ones accepted by the automaton. Right?
Okay. So why don't you do the step case first, and then I'll do the base case. Does that make sense? So we're going to go inductively on J's. That's the whole idea, is to build up, to make things more complicated a little bit at a time by saying, well, first of all, you're not allowed any, and then you're allowed this state, and then you're allowed more. So, so we say inductively J's from J's, and then I'm going to choose better names. And I'm going to suggest that we do the step case first, or rather that Fred does the step case first.
So it's usually a good idea to do the, well, you call it the step case, but really it's the base case of the induction, right? So it's the case where we are not allowed to pass through any intermediate states.
That was more, I was actually suggesting that you do the step
case.
case.
Oh, I see. You did mean the step case. Okay. Yes. It's confusing because this is the one where you actually describe the steps. Right?
Yes, one is talking about single steps and the other is talking about...
Sorry. Okay. So we do the step case of the induction. So this is the case where we are allowed to pass through J and X's. And inductively, we can assume that we've already solved the case for X's. So we know we have a definition of route via X's, anything we want, right? So let's think about this. We just lost the picture. But if I want to go from here to here via some other state, well, then what I could do is, so I have my first state I could pass through J. So if this is my J, then of course I could go to J, and then I could really go from J to J as many times as I want, right? Which in this case would just be this loop. But then if I in the end want to end up at K, if that's this one, then I also have to go from J to K in the end, right? So I think a reasonable strategy here is to say, well, you're allowed to go from J to I, from I to J, then you can loop around at J if you want. But then in the end, you need to go from J to K. And if you can do all of this, then you can overall go from I to K, right? So let's see if we can describe this. So I want the regex for this. So first, I want to go from I to J. Well, I have a function which describes regexes a regex for going from I to j, right? That's the root via, and I don't want to pass through j on the way. That would be weird. So I'm just going to exclude that by saying I'm allowed to go through x's, but not through j, right? And I'm going to from I to k. So that's going to be one big regex that describes all the ways to go from I to k, passing through x's. So that's going to take me to my j state.
Yes.
And then,
Yeah, hang on.
Yeah.
Careful. I to k via x is sure, but that's getting up the way.
Sorry,
But,
I to j is what I meant. Yeah.
Right. Yes. So you've got to, so this thing in particular describes how to make our first visit to J, right? On our first visit to J, we haven't been through J yet. We've only been through the other stuff.
Yeah. And because we are allowed to pass through x's, but J is not in x's, we are assuming, right? Then really we're going to go from I to j without passing through j on the way, right? Okay, so that's how to get from I to j. And then I'm going to loop around from j to j. So looping around is what the star expression describes. So I'm going to say root via xs jj. That's going to compute some big regex that describes how can I go from j to j passing through x's, right? And the star says I'm allowed to loop around as many times as I want. Yeah.
All right.
Okay, but now it's back. Yep. Thanks. Please shout out rather than saying it went off 20 minutes ago. I thought that was great. Yeah. Okay, so this is describing going around from j to j as many times as I want, right? That's what the star says. Could be 0 times, could be 17 times. But if I want to end up at k in the end, then after I've done my looping around, then I also have to finish by going root via xs from j to k. Right?
Color error.
Am I allowed to put this in a new line? I guess I am.
Yes.
Yeah.
Usual indentation rules apply.
Yeah. Okay. So this is saying, okay, we're going to do it in kind of 3 stages, right? Go from I to j, go from j to j as many times as you want, and then go from j to k. So it's going to produce these and the star, but we don't know how the individual steps in these journeys are going to go, right? So we really need the base case to describe that.
Right, you've forgotten something though. Right, the thing you've described is how to get from I to K for a journey that has a first visit to J and a last visit to J. But it's still conceivable that we might get from I to K not using our freedom to go through J at all.
Right, yes.
So you have to include that possibility
I've
that we get from I to K.
Forgotten something important, which is I could make it all the way from I to K using just the x's, not passing through J at all, right? So I could just say, well, I could go passing through x's from I to K. That's, again, fine because x's is smaller, so I know how to describe these things. Or I'm actually passing through J, right? So I'm saying, what does it mean to go from I to K passing through these things? And I'm saying, well, either I'm not going to go for J at all. That's just this recursive call. Or I am going to go through J, and this is how that would go, right? I would first go to J, then I would loop around, and then I would leave J.
Okay. So that's how we build things up. That's how we add an extra possibility to the roots that we're building. Now we have to explain how to kick it off. So here, our list of states that we are allowed to put in between is empty. So we are not allowed to consider words, strings longer than 2, because that would involve some intermediate states. We are allowed to consider strings of length 1 and strings of length 0. So there's nothing for it but to do a from fest and just get all the combinations. Right. And now our mission is to turn the picture into the program. So let's look at the picture. We are being asked, what are the 0 or 1 length paths between any start and finish points? That's the question we're being asked, right? So,
Or, I mean, put slightly differently, we're being asked, how can we go from one state to another without passing through any intermediate states? The only way you can do that is by a 0 length string or a 1 length string, right?
yes.
As soon as you have a 2 length string, you need to go to some other state in between.
Yeah, so we have to describe those possibilities. Okay, so how do we get from 0 to 0? You have to ask yourself 2 questions. Does staying still work? Does eating a symbol work? Right. 0 to 0 in 1 step. Can you do that by eating a symbol? No. But you can definitely do it by staying still. So the regular expression which describes that is null. Okay? 0 to 1. Can you do that by staying still? No, they're different. Can you do it by eating a symbol? Yes. Which symbol? A. So that's described by eat the symbol A. Going from 1 to 0, can you do that by staying still? No, they're different. Can you do it by eating a symbol? Which symbols will do? Yeah. So that's sim B or sim C. And lastly, how about getting from 1 to 1? Can you do it by staying still? Yes. Can you do it by eating a symbol? Also yes. Okay. So what we've done, you can see the base cases of this program are really just a translation of the diagram. We're just saying what's adjacent to what, which loops exist in the picture. Okay. So let's uncomment out the test, and you also need to delete the old answer. And there we are. We get a big, ugly, I mean, I've seen bigger and uglier regular expression. And you can see, let's chop it up a bit. Thank goodness for Emacs showing where brackets finish. So there's, let me see if I can tidy this up a bit. Right. Okay. So you can see we ended up with 2 possibilities. You can see the structure of the construction right, actually, so it builds up by saying, to get from 0 to 0, your first possibility is just to stay still. Your second possibility is to eat an A, go to 1, eat some more A's, and then come back with a B or a C. So that's kind of one loop round. So that in particular goes via 1, but it does not go via 0. And then here we're saying, well, you know, actually, you could do 0 or more loops round, or rather, yeah, you could either stay still or loop round to get to 0. And then you can loop round some more from 0 to 0. And then you can get from 0 to 0. So you can do, yeah, so you can see there's an awful lot of redundancy in this second, or rather, well, we should number them 0, 1, 2, right? So this option is full of redundancy. Okay. So just to take you back to the homework, which of course I can't click on because Zoom has put a stupid thing in the way. Zoom is like a cat. It always knows what you want to click on. Right, so one of these is the homework. Maybe they're all in the homework. So you notice, actually, that our base cases were all lists of essentially a big OR of choices. And that's often the way with these things. So I've given you a leg up to manage that by saying, well, let's not work with regular expressions that represent choices using the regular expression or and the regular expression fail. Let's just work with lists of choices, which you can concatenate to offer more choices. So we give you lists and we give you concatenation. And then I'm giving you this operation, which takes 2 lists of regular expressions and generates all the ways of saying something from the first list, then something from the second list. So that's how you combine a bunch of choices to start and a bunch of choices to finish. You can see I've done it by saying, well, if there's no choices for the front, then there's no choices. And if you have P or the rest of them, then you can either do P and then something from Q's or something from P's prime and something for Q's. So we're generating all possible combinations. But crucially, we never generate regular expressions that say fail then something, which are kind of useless. So this is my first step towards helping you tidy this stuff up, but I'm hoping that you will do the rest. And you'll notice, so you can see in this picture, if I can find the picture, the accepting states of the NFA are 0 or 1. So correspondingly, the accepting states of the DFA are any set which intersects with 0 or 1. So it's the set of 0 and the set of 1 or 2. Right. So the test at the end, says the start state is the set of 0. So I'm saying, give me the roots via all states from 0 to 0, together with the roots via all states from 0 to 1 or 2, and then this choose from at the end does one final thing, taking a list of choices and turning it back into a regular expression by saying, well, we turn the empty list into fill, and we if we've got q cons q's, we turn that into q or the regular expression we get from q's using the clever or. So in particular, this is going to finish with or fail if there's a non-empty list. And or fail is redundant. So one job you should do when you're improving this definition is definitely, if Q is fail, you just want to give back P, and that would get rid of the or fail that choose from is putting in at the end of the list. So that's an introduction to your homework. And you can see also back in the picture that although I haven't drawn any arrows into the empty set is effectively the trap. So there are some states from which there are no ways to consume certain symbols, and that means the set of places you could possibly get to by consuming a symbol, that symbol is empty. So to build the DFA properly, we need to include the trap, and that's what I did in this table. So for example, if you're in state 2, then the only thing you can do is eat an A. You can't have a B or a C, which means if a B or a C turns up, you're in the trap. So that's why the set of states here include the trap state, the set containing only 0, the set containing only 2, and the set containing 1 and 2. And then here's your all states, which includes all of those options. Okay, it's 9:48. We've got to the end of a topic. Looks like half time to me. See you at 2 minutes to.
I think that's only that's pausing the sharing, but
Oh,
it's a good experiment.
June. Okay. The puzzle we're going to think about in this half of the lecture is the puzzle of recognizing when a string which consists of 0 or more open brackets and close brackets has proper bracket balancing. So that every open bracket is balanced by its own corresponding closed bracket. And I thought I'd show that we can certainly write a silly sentences grammar for strings which are bracket balanced. We observe that the empty string is bracket balanced because all the brackets in it, all the open brackets in the empty string are matched by closed brackets. Typical mathematician vacuous satisfaction joke. We also notice that if you've got 2 bracket balanced strings and you put them side by side, what you get is definitely bracket balanced. And if you've got a bracket balanced string, you can wrap it in an open bracket and a closed bracket, and you'll get a bigger bracket balanced string. Okay, so let's just check, for example, that we can, oh, no, that's fine. So these these two should be happy. So this one goes by this rule. And now I have to explain why what's in the middle, which is nothing, is okay. And that's by the rule that's empty. Oh, I have to say parse B empty string. I have to say what the thing is. And now it's happy. Okay. And then same deal here, slightly more involved. So the thing I'm going to try and parse is the contents of the outer brackets. And that looks like a pair to me. And then my two components are these things. Yeah. And here I...
Close that string, please.
Yes, I could close that string, and now it's happy to put question marks in. And then what I do, given that I already did the empty bracket, I paste the old stuff in, fix up the indentation. We really must get the syntax highlighting for this stuff. And now it's happy. Okay. Now, for this one, we could make a start using this rule. But then that now you can see we're in trouble. I mean, we could split it up. We could defer the trouble.
Looks like a pair, right?
Looks like a pair. You know, okay so far. But now, well, we're in trouble. I mean, we could say, oh, looks like a pair, and we could keep saying looks like a pair, but we're never going to do anything that eats that solitary open parenthesis. So we're a bit stuffed.
Which we should be. I mean,
Yes.
we tried to parse a non-bracketed string with a parser for bracketed strings, right? So it's not like it went wrong. It went right by us not being able to complete the parse.
Yes, works as intended, won't fix. Okay, but this shows that, I mean, this is the statement of the problem. We are doing the computation here of checking whether a string of parentheses is properly balanced between opens and closes. And there's every reason why this is an interesting problem. In fact, there's lots of stuff that shows up in graph theory that involves this. But never mind that. Most programming languages insist on balanced brackets. And it's a very common source of syntax errors. So, you know, it's really nice that this editor that we're using, Emacs, even tells you, you know, when you reach one parenthesis, it highlights the other one, which is a great help for making sure you're saying what you mean. And one thing you will find as you get older and work in this business more is that your brain just does this. Your brain will contain a machine for checking that brackets are properly balanced. And when somebody casually leaves off a closing parenthesis when they're giving a presentation or a lecture, you will notice and be immensely irritated at them until they fix it.
Hence me asking Connor to close that quote.
Yes. So so that's so this is a thing that we ought to be able to do. And one question we might be interested in is how. So do you want to do the program, or shall I do it?
Why don't you do it?
Okay. So I'm just going to use bits to represent brackets because I'm too lazy to define another type. So I'm going to use O for open and I for close, and I've got a list of bits, and I want to say, haha, false for not balanced and true for balanced. So, however, I'm going to need to keep some working information as I go along, working my way from left to right along this list. Any suggestions for what I ought to remember? How would you do it? You're reading from left to right. Yeah. The number of open brackets that you haven't got around to closing yet looks like an excellent suggestion. So that's why I seeded the file with numbers. So
could we actually very quickly define a new data type for the brackets?
Oh, okay. Fine.
Just so we don't confuse what the bits are for, right?
Remove the out-of-date comment. Out-of-date comments cause so much havoc. Okay. Fine. And I'll update the lecture file as well. So the plan is that we're actually going to write a function called which remembers how many brackets are still open, and now we're going to define balanced B's to be still open 0 B's. And now we have to define still open, what's still open, N B's. Okay. So we're going to work our way along B's. The number is going to go up and down a bit, but we kick off with no brackets open, and let's see what happens. So we're going to go inductively on B's, and we're going to look at B's. Okay, now, if we have reached the end, when are we happy? When are we sad? It depends on N. Let's look at N. Right. So if N is 0, that means there are no brackets still open. We've reached the end. We're happy. Meanwhile, if we reach the end and there is at least one bracket still open, we are sad. Okay. Right. In the non-empty case, we better see what shape of bracket we've got. If it's an open bracket, then all we have to do is move along and remember that there's one more open bracket than there used to be. What about if it's a closed bracket? What do we do? What do we care about? Can we always close a bracket? We better not close a bracket that isn't open. So we better check N. If there are no brackets open and we see a close, we are sad. But if there is a bracket open, we've closed it, and now there's one fewer open. Okay, so that's our function. We could even run it. So what did we have? Let's actually do the same examples. So we had open, then close, then nil. And that's true. Let's not have any tresting. Balanced. Open, open, close, open, close, close, nil. That's also balanced. But if we remove the last closing parenthesis, that's not balanced. Okay. So we have been able, you've seen it before your very eyes. We haven't done any proofs about it or anything, but we have been able to write a program which, if we thought about it, we could prove, did indeed decide exactly whether its input consists of balanced parentheses. Now, the question is, can we write a regular expression that characterizes balanced parentheses, or equivalently define an automaton, a finite state automaton that recognizes balanced parentheses? And you should already have some intuition about the answer to that question, given that what we decided to remember as we worked our way along the input was a number. And numbers can get awfully big, whereas the number of states in a finite automaton is stubbornly fixed. Might be large, but it doesn't get bigger in the way that numbers do. So that does rather suggest we might have a problem.
Yeah, maybe.
Maybe.
Let's try.
Let's give it a go.
I mean, it's the kind of thing that regexes do, right? I mean, we have some strings and we want to say which strings are we happy with, which strings are we not happy with. So it makes sense to ask the question. It's not saying, can you write a regex that displays your favorite post on Facebook, right? It's actually trying to match on strings. So let's see.
Don't.
So I'll try to do a DFA or an NFA maybe, because it's a bit easier to think that way, right? Even if it's the same thing as a regex, if you can do it visually, then it's probably easier. So, okay, let's see how I would try to do it. So, well, there needs to be a start state. Have that. And, well, if I get no input, then that's a balanced bracket, right? So my start state is also going to be a finishing state. That's fine. But then I have to say, what happens if I actually get some input, right? So, okay, there's two possibilities, right? I could get an open bracket, put these in quotes to make it look less like a C. Or I could get a closing bracket, right? Well, if I get a closing bracket, then from this start state, then I should just fail, right? So this is going to be my trap state. And well, I could just loop around here forever for anything. And I'm not going to make it good, right? If I get an open bracket, then I still have a chance to succeed, right? Because if I now get a closing bracket, then I'm happy again. If I get a closing bracket, I can go back to my original state, right? But if I get another open bracket, then I should not go back here because I haven't balanced things. Now I have two things I need to close. So I better go to another state. Okay, and if I get a closing bracket here, well, then I've closed one of my opening brackets, so I can go back here, right? And if I get another one, and I go back here and I'm happy, that's fine. And if I get another open, then I go here and now I have to close one more, that's fine, right? But the problem is, what happens if I get another open here? Well, then I should remember that I have one more to close, right? Which I can do by going back. But it looks like I'm just building up this infinite chain, and unfortunately, I don't have a finite number of states anymore, right? I need an infinite number of states in order to deal with all the strings.
Right.
So this didn't seem to work, but maybe it's just because I'm stupid. Maybe there's some better way to do it. I don't know.
Right. Let's put the close bracket in there. Thanks for winding us up. But yes, you can see that wherever Fred stops, we just have to do one more open bracket, and that's a correct string, a potentially correct string that is we're going to say no to. We're going to be sad when we could have been happy, and that's never good.
So that shows that this machine doesn't work.
Yes,
right?
we've got one strategy that we've attempted that didn't work out. However, that's frustrating, but it's not enough to say that the problem can't be solved, just that we're too stupid to solve it. This strategy hasn't worked out for us. How would we prove that there's definitely no way to do it? That anyone who claims to have built a DFA to solve this problem is a liar. Well, sometimes you need some useful tools. So we're going to show you a thing about DFAs, and then you can transfer it to NFAs, regular expressions, called the pumping lemma. I don't know if we've had the word lemma so far. When we say prove stuff, right? Stuff you prove. There are fancy Greek words that means stuff that has been proven, right? So there's a word theorem. A theorem is something which has been proven. And a lemma also means something that has been proven. But there's a kind, as well as that direct meaning, there are connotations to these words. And generally, the idea is that a theorem is supposed to be something important. A theorem's supposed to be an achievement, you know, whereas lemmas are supposed to be useful equipment on the way to the achievement. And yeah, so the fact that the pumping lemma is called the pumping lemma is a clue that it's meant to be useful for doing other stuff. And in particular, the pumping lemma is going to be useful for showing that this problem's impossible. So that's the thing, actually. You use the pumping lemma as a tool for demonstrating that some things can't be done with DFAs. Okay.
And it's almost always harder to show that something can't be done, right? Because to show that something can be done, you just do it.
Yes. It's always, you know, there's some, there are two games to play in this life. There's the keep the balloon inflated game, and there's the burst the balloon game. You know, bursting the balloon, one pin once. Right. Keeping the balloon inflated involves staying away from all the pins. Right. So that's why so this is very definitely this is a balloon game, so we're going to need some technology. Okay. So let's see if we can actually, let's go back to here, right? Here's a DFA with two states. Right. The pumping lemma states, or the pumping lemma says that given that this has two states, is that if you give me a string accepted by this automaton that has length at least 2, because 2 is the number of states, I can find a chunk of that string. I mean, actually, any string that's accepted that's of length at least 2, I can find a substring within the first 2 that I can either cut out or repeat in situ, and the machine will still accept all those words. So let's have an example of that before we get any weirder, right? So let's pick a string which this, oh, am I off the screen? I'm off the screen. What I want to do is get that back there and here, right? Okay. So I will pick a string that this thing accepts. Let's say do we agree that this string of length 5 is accepted? Absolutely. Right.
Let's walk around the machine.
I was, yes. So, well, what I was actually going to do was in between, well, at the beginning, we started state 0. Right. And then the first A takes us to state 1. And the second A takes us still to state 1. And then we go to 0. Oh, should I have stopped sharing? Yeah, should have stopped sharing. Sorry, Zoom. Also, sorry, video. Right. So we've got our diagram. We've got our string so far. We got back to 0. Then we went to 1, and then we went to 0, and we were happy. Okay. So now the trick for the pumping lemma is to say, well, let's just look at what got us the first two steps. So that's this sequence. I claim that this sequence contains a loop. And you can see it contains a loop.
Because it goes from 1 to 1. Yes.
Yes.
Just to point out what the loop is.
So here's our loop. And what that means is that we didn't actually have to do that at all. Or we could do it any number of times. So that means we can also accept A, C, A, B, and A, C, A, B, and A, C, A, B. So that's no times round the loop, once round the loop, twice round the loop, and so on. So what we're saying is that we found a substring within the first n steps, in this case 2, that we can pump. That's to say, we can keep going around as many times as we like. So right, and that's because if you've got n states, you've got to start somewhere, and every time you take a step, you're basically playing the snake game, right? You know, if you want to avoid being pumped, you've got to stay away from states you've already been to. And you start off in one already. By the time you have eaten n symbols, you have visited n+1 states. And if they're all different, that means you've managed to choose n+1 different things from the n things which are available. And as you proved last semester, choosing successor of n things from n things happens in 0 ways. So congratulations, you have already proven the pumping lemma. And this is, this is an example of it. So what we do, or do you want to deliver the killer blow?
No, I'm still hopeful that maybe
you're still hopeful. Okay, then I'll be bad cop. Right. So Fred thinks he has a DFA that solves the bracket balancing problem.
Not today, but maybe yes. Soon I'll have one.
Yeah. Well, why don't you at least guess how many states it has?
Yeah, I think it will have 10,004 states.
Right. Well, I don't have that much pen.
Okay. I think it'll have 5 states.
Okay, thank you. Right. Well, I have every confidence in Fred. So I'm sure that Fred's machine will accept right. That's 5 opens, 5 closes.
Yeah, so it matches. So clearly my machine will
absolutely.
It. Yeah,
fantastic. Right. But the pumping lemma says that I can find in the first 5, I can find a non-empty substring that I can either delete or repeat as many times as I like. So somewhere in here, there'll be a non-empty segment, maybe even a short one, that corresponds to the automaton going into a loop where, given that this already matches, I can delete that and it will still match. So sorry, although it got this this example right, when I delete one open, it says yes to that as well.
So I guess there can't be any such machine then, right?
Yes. So pumping lemma says, the pumping lemma tells us how to construct a counterexample to this problem. So we know that although we wrote a little program that solves this problem, we can't build an automaton or write a regular expression to do it. And in general, that's the situation. One reason why we actually told you about grammars in the first place is that grammars are more powerful than regular expressions. Because, well, we've seen in an example. Again, the point here is that no matter how many states you've got available, it's not enough states to remember how many closed brackets you're waiting for. So, you know, that's that's what the pumping lemma brought home. So we've so it's kind of funny because you know, ironic, because, you know, what is this thing? This thing is a very large finite state automaton. It's got, you know, a hugely exponential but finite number of possible states it can be in, because it's got, you know, several gigabytes of bits that can be 0 or 1. You know, essentially, as far as we work conceptually, the finiteness of this machine is completely useless as a way of figuring out what things we can do with it, you know, apart from things like integer overflow, and stuff like that. Yeah, so if we're trying to figure out how to, you know, manage computation conceptually, automata are useful things for talking about cheap computations, but some computations are a little bit more expensive. We need to look elsewhere for something general.
So one difference between a computer and a finite automaton is that even though right now this is a finite machine, right? It has 16 gigabytes of RAM, whatever it is. But you could imagine installing more RAM into the computer, right?
Yes.
So you start your program, then you check your system usage, and you realize, oh shit, I'm running out of RAM. Right, so just quickly go to the store, buy some more RAM, plug it in.
Yes.
And then my finite state's a bit bigger, and I can keep doing this.
Yes.
Which is not something you can do with a DFA. Right?
Yeah, and indeed we are connected to the internet. And if I was a sufficiently cunning hacker, I could commandeer computing resources from any other computer on the internet, and computers are being built and connected to the internet continuously and rather rapidly. The amount of states of computers connected to the internet has increased significantly during the course of this lecture. You know, we essentially are saying, you know, how many that we're bounded by the resources that we can use to build things and network them. And, you know, and when we've exhausted the Earth, we'll doubtless start mining for the appropriate minerals on the moon, and burying all our plastic tap in the holes we leave behind. And we'll just, you know, keep going. So this sort of finiteness is it's a fleeting illusion, or at least it's always replaced by larger but still finite. And that's actually the key to one of the earliest formulations of what it is in general to be a computer. And that's where we're going next. We're going to tell you about an extension of the notion of finite state automaton called a Turing machine, after the mathematician Alan Turing, who was around in the early part of the 20th century. He's famous for cracking Enigma, right? He didn't crack Enigma. The Poles cracked Enigma before the war. Before Hitler invaded Poland, the Polish mathematicians who knew how Enigma worked were successfully brought to Britain, where they explained, in theory, how to crack Enigma. What Turing did was built a machine to do those calculations fast enough that it was actually realistic to crack the signals that were coming in. That's the amazing thing. It's not the mathematics of cracking Enigma, that what Turing's contribution was to build the machine that made it realistic. So it's important that Turing is remembered for what he actually did. And it's also important to remember how the authorities treated him. But anyhow, what's a Turing machine? It's got some similarities to a finite state automaton, in that a Turing machine has a fixed number, a fixed and finite number of control states, as we now call them. But where in a DFA, that's the only memory you've got. In a Turing machine, you have an infinitely extensible memory that's associated with the machine. And actually, that's where the symbols live. Instead of the symbols arriving one at a time from some input, they start already preloaded into the memory of the Turing machine. And like the memory of the computers we have today, that memory is mutable. And we say it's, so we're still working on an alphabet of symbols. So I'm going to draw our alphabet of symbols, since I've got paper. I'm going to let the blank be a blank. There's always a blank symbol. And then we're going to have our open parenthesis. We're going to have a closing parenthesis. And I'm going to allow myself an extra symbol that I'm allowed to use to manage the process. Okay, so any given time, we've got a tape. You can imagine just a big, long, imagine an enormous toilet roll. An infinite toilet roll. In fact, a toilet roll scroll. It's rolled up at both ends. And on each page of toilet roll, you've got one of these symbols. So what we're saying is that the Turing machine has a tape head through which we are looking at one symbol that is currently on the tape. And by convention, the Turing machine will start with the leftmost non-blank symbol. How do I know there is one? Aha, that's another promise we make you, is that if you go far enough in either direction from your current tape head position, you will eventually find, you won't be able to test this for yourself, but we make you the promise that that eventually the rest of the tape is blank. So that's to say, there is a potential infinite supply of memory, but you've only used a finite amount so far. So if we are in this situation, we might have an open, close, open, close, close. Okay.
So to put it slightly differently, when we get the input, we are guaranteed that the input is finite, right?
Yes.
We're not going to have the whole tape filled up forever. It's going to stop at some point.
Right.
And then we'll see that the things we can do, we're never going to be able to fill up the whole tape after that.
Yes. Right. So infinity is sometimes a tricky concept. For example, is it possible to test whether the tape is entirely blank? I mean, we could kind of go on a wander. I mean, okay, I haven't said something important. Right. Rules of the game. The information at any given time that the Turing machine has are the current control state it's in and the symbol it can see through the tape head. So can see state and symbol at tape head. Can choose new symbol at tape head. Move left one, right one, or stay still. And new state.
Time to move up.
So that's what happens. So there's a fixed program that says, given the current state and the current symbol, what do we overwrite this symbol with? Do we move left or right or stay put? And what state do we move into? And there's a special state called the halt state, which means the program's done. So here's the thing. Turing machines do not promise to give you an answer. You can put them into a flat spin. And that's you know, most of the programming languages that you work with can do that. So for example, in Java, nothing stops you writing while true empty curly braces. And that program will be gently warming for quite a while. So yes, that's the reality of programming as we know it, that in order to allow us to do sensible things, it also allows us to do stupid things. Okay. So how long have we got? Maybe 10 minutes or so. Do we think we can define a Turing machine that will recognize balanced brackets? Oh, okay. I'm going to add one more convention, which is that. So, okay, I've already specified that when we start with the tape head at the leftmost symbol in the input, right? And if we stop, the convention is if we stop on a blank, we're happy. If we halt on a blank, we're happy. If we halt on a non-blank, we're sad. Because we can't test if the whole input's blank, can we? So we have to make our decision about happiness or sadness on the basis of something we can actually test. Okay. Do you want to have a go?
I don't know. I wanted to point out a few things. So,
sure.
I mean, just to comment on the language, just in case. So, can choose here, in some sense, really means must choose.
Yes.
Right? So there's a number of fixed steps the machine goes through. So it's given, it can see the state and the symbol at the tape head. And then to move to the next step, it has to choose a new symbol, which of course could be the old symbol. So it doesn't have to change the symbol. It can philosophically change it to the same thing it was, which is no change at all. And similarly, it doesn't need to choose a different control state. It could stay in the same state, but it has to say, what is this control state after I've done this step, right? But it can choose to stay still. That's different, right? Moving left, moving right, or staying still, that's a choice you have to make.
Yeah.
And this is how you run it, right? You keep doing this until you halt.
Or forever.
And if you never halt, then you're going to do this for a long time, right? So I guess we could get back to the question, can you have a machine that detects if the whole tape is blank or not?
Yes.
So you can certainly have a machine that looks at the current position. If it's blank, if it's not blank, then we can stop and signal that it's not blank. Then our convention was a bit annoying because we said we were happy if it was not blank, but here we should rather signal non-happiness, right?
Well, maybe we're hoping that it's all blank, right?
Yeah.
So if we find something that's not blank, then we're unhappy.
Yeah. Okay. Right. So we can detect if it's not blank. But if it is blank, then what we have to do is we have to keep moving, right? Left or right. We could finish all of the infinite states to the right first, and then we could hope to go back to the ones to the left, or the other way around. Either way, we're not going to be able to look at them all and stop in a finite amount of time. Right?
Yes. The devil could just have hidden the blank symbol a little bit further away. So yeah, that's a puzzle we can't solve.
And it's not because of the left-right thing, right? Because you could also imagine kind of dovetailing, looking to the right, and then I look one to the left, then I look two to the right and two to the left, and so on. It's just that there's just a lot of positions to check.
Yeah, but you would need a marker. You'd need to leave yourself a little trail of all the places you've been, and each time you'd have to go a little bit further. And actually, that's a useful thing to think about. What our strategy might be for balancing the brackets. As here we know. Well, I mean, so we're promised, by the way, that so this is crucial, that there are no gaps between the brackets, that our opening opening sequence. I mean, I suppose we could allow it to contain dots, but
so we are promised that all that's going to appear on the tape are the things from the alphabet, right? No one's going to throw in a surprise Unicode character there, right?
Right. Okay. So there's going to be a stick. Maybe I'll just keep that there. There's going to be a start state. I'm going to make states a funny color. Right. So there's going to be a start state. And we have to say what happens for each of our blank left open close dot. 4 possible symbols we could see. I should have drawn that in purple, really, shouldn't I? At the tape head. Okay, so we need to figure out what our strategy is. I mean, it's a bit of a rabbit out of the hat, but if we start worrying, it's difficult. We could see an open parenthesis and think, okay, maybe I should go looking for the closed thing that matches it. But then I have to keep a careful count of the stuff in the middle. And it's not easy for me to do that counting because I've only got finitely many control states, and my only memory is the tape that I'm working on. Whereas if instead we just go looking for a closing parenthesis, then we know we must have passed its corresponding open. So our plan is to start by heading rightwards, looking for a closing parenthesis. And that tells us that if we see an open parenthesis, we want to keep the open parenthesis. We want to move, I'm going to write +1 for go right. And we want to stay in the same mode. We're still searching for a closing parenthesis. So that's start. Chose the wrong shade of pink. Never mind. And likewise for the dot, we're going to leave a dot. We're going to go right. And we're still searching.
So Connie, you haven't explained what you're going to do with the dots yet.
Right. Well, I will in just a moment.
Yeah.
Okay. So the idea is that I want to successively overwrite matching pairs of parentheses with dots. A dot instead of the close, a dot instead of the open, until there are none left. Okay. So that means that if I see a closing parenthesis, I should replace it with a dot, and I should go left. And moreover, I should now be searching for an open. So we better have another kind of state. So that's, I'm going to call that state match. Okay, we've still got one more decision to make. If we find a blank, we've been moving rightwards. We find a blank, that means we've hit the end of the input. So now we have to decide what to do. Are we happy? Well, we might get, the input might consist of a bunch of open parens and then a blank. And if we were just sailing past those open parens, we hit the blank, we're not done. We have to make sure we've got them all. So we hit the blank, we leave a blank, we switch to moving left, and now we are tidying up. We hope we're just going to get a load of dots. I'm going to call that tidy. Okay. So we're in the match state. Now we have to say what to do in the match state. And I will get the color schemes correct. Maybe Fred, you want to do this bit?
Mm-hmm. Okay, so we just have to describe what's happening when we're in a match state and we see each of the possible inputs, right? So remember, in the match state, we are kind of moving leftwards, trying to find a matching open paren for the closing paren we found. So if we find an open paren, well, then we're happy, right? Locally happy. So we can replace this open paren with a dot. And then we can keep going and continue trying to match new things. So we move to the right. And I guess we can just go back to the start state.
I believe so. I notice we're about to leave a cliffhanger because it's 5-2.
Yeah. Right, should we finish match? Do we have time for this?
Yes, I think you
Yeah.
probably just about do.
Yeah. Okay, so let's see if we see another closing paren. That shouldn't really happen, right? Because we started going back as soon as we found the first one here. But just in case, I guess we just leave it in place and continue looking.
No, we're unhappy to
Ah,
see a closing paren.
right, because we want them to match, but here we looking for an open that matches this one. But instead we found another closing one.
I mean, we found it should never happen, actually. It should be academic because our algorithm involves finding the leftmost closing parenthesis.
Yeah.
So if we see a closing parenthesis, it means that whoever it was kicked us off didn't put the tape head at the leftmost input.
Which isn't happening. So, okay, but
we should moan.
Let's
be
be defensive. Yeah. So in this case, I'm going to leave an empty thing on the tape. I'm going to stay still and I'm going to hold.
Well, hang on a minute. We're unhappy, so you should leave a symbol.
Ah, sorry, I got the convention wrong.
Yes.
Okay.
Yeah.
So I leave a symbol and just leave the same thing then.
Yeah.
If I say a dot, then that could be because previously we matched two things and then I should just move along it. So if I say a dot, then I'm going to leave it in place. I'm going to keep moving left and I'm going to keep matching. And finally, if I see an empty space, that means I've gotten all the way to the start of the input, which means that I didn't find a matching bracket. So in this case, again, I should be unhappy. So I'm going to leave a dot, I guess. I'm going to stay still and I'm going to hold. The signal that we failed, right? We didn't find a matching bracket. So in this case, we can stop with our convention for saying wrong, return false.
Right. But as it's 2 minutes to, we had better leave how tidying works as a cliffhanger for next week and wish you an excellent weekend. Have fun.